We need to be able to explain the trends of first ionization energy. That is the energy that you need to remove the outermost electron or valence electron from the atom, which is held by electrostatic attraction of the nucleus. Now this force that you need to overcome depends on two main factors, and there is one factor that we use as fine-tuning and to argue the case. The first main factor is the charge of the nucleus, or the nuclear charge. Simply put, number of protons within an atom. Now as nuclear charge gets higher, increases, that makes your ionization energy to go higher as well. You need more energy to remove an electron that has more protons holding onto it. The second important factor is the distance between the valence electron and the nucleus, or the size of the atom. Now this time, as the atom gets bigger, you need lesser energy to remove the electron because it's further away from the nucleus and cannot be held as strongly. To fine-tune and argue, we need to also look at the electrons that are laid between the valence electron and the nucleus, the inner electrons, and that introduce a shielding factor. So let's just look at it. Let's look at the first three periods of periodic table. Now the data is always given to you, and then you need to justify it. Let's just look at hydrogen versus helium. Helium has the most ionization energy among all the elements. So hydrogen is 1312 while helium is 2372. For all your cases, you should write your electron configuration. Hydrogen is 1s1 and helium is 1s2. Now hydrogen has 1 plus as your nuclear charge, helium has 2 plus. So this obviously has higher nuclear charge. It's strongly held. Therefore you have more difficulty removing it, you need more energy. So the simple argument is higher nuclear charge. You could also after go as size and say this also is smaller in radius, closer to the nucleus, but the nuclear charge is better argument. So hydrogen is lower than helium because helium has higher nuclear charge. Now, once you go to the second period, there's a humongous drop. You come to lithium. Lithium is only 520 kilojoules. The question is why? Then we lay out electron configuration, 1s2, 2s1. You have more nuclear charge, so that could not be a good argument. You should go after the size and say 2s is further away from the nucleus, therefore it's easier to remove. So size is your argument. Size goes higher, the valence electrons are further away. Therefore, it's easier to remove them. So lithium compared to helium is because of the size. Now let's just go to the next member on this period, beryllium, which is 1s2, 2s2, 4 plus. Now they have the same subshell, therefore the size is not a good argument. The argument for this is simply nuclear charge. You have higher nuclear charge. Now there are anomalies that take place. The first anomaly is between beryllium and boron. There is a drop. If you look at beryllium is 899, boron is 800. The question is why? So what we do as usual, write your electron configuration and see what comes in its difference. 2p sub 1. And you have 5 plus. If you go after nuclear charge, you cannot defend it. It's higher nuclear charge. So what you should go is after size. The 2p is further away from the nucleus, or you could also go after inner electron and shielding. The 2p is being shielded. So here I have two possible arguments. One is 2p, electron is further away. And number two is that 2p is also being shielded by 2s electrons, while here the 2s is not shielded. So that's your another argument. So the first anomaly or exception is when you go between group 2 and group 3, beryllium to boron. Same thing gets repeated in magnesium and aluminum. Simply go after further away or size. Now we go back to our norm, which carbon And nitrogen, they simply have more nuclear charge. So if you do carbon, it's 1s2, 2s2, 2p2, 6 plus. So it makes sense. You have higher nuclear charge, therefore higher ionization energy. Same thing with nitrogen. It's 1s2, 2s2, 2p3, and therefore you have 7 plus, higher nuclear charge, so it increases. But now second anomaly comes to life. Between group 5 and group 6, you see there is almost a drop or stagnant. Nothing is happening. Nitrogen to oxygen. Why? We need to be able to justify it. So what I'm going to do for nitrogen is I'm going to show the 2p in terms of its orbitals. So for nitrogen, if you do the 2p, there is 2p sub x, 2p sub y, and 2p sub z. If we respect Hund's rule, there are 1 electron in each of these orbitals, and they go singly with spin up. Now, if you look at oxygen, which has 8 protons, should have higher nucleus and higher number, but it doesn't. It actually decreases. If we do its electron configuration, remember it's 1s2, 2s2, 2p4, 2p4. Let's just dissect this and see what's coming to our yield. So I have 3 degenerate orbitals, 2p sub x, 2p sub y, 2p sub z, 1, 2, 3. The fourth electron, I'm going to put it here. Now the only argument and the right argument is these 2 electrons are repelling each other. They're like charges. And the repulsion is felt by the last electron, so it's easier to snap it off. So the argument here between group 5 and group 6 is simply this fact that it's electron to electron repulsion. Therefore, this repulsion is being felt by the electrons here, and it's easier to snap this electron off. So that's where you need to be gentle, and that's fine-tuning the last factor. Then we go back to our norm, and nuclear charge is the only answer. If you look at fluorine, it's 9 plus, and it's 1s2, 2s2, 2p sub 5. So the argument is nuclear charge against oxygen. And finally, you go back to your noble gases. They always have the largest ionization energy in that period. It's 1s2, 2s2, 2p6. They have the same size, so the nuclear charge is your argument. So from here to here is nuclear charge. So practice this. Look at anomalies, because every time you walk into exam, IB teachers, they love to look at exceptions and challenge you on that. Why are there drops rather than a normal increase?